and get water. Okay. We start recording here. Share our screen. Share. Okay. Our lecture today, well, actually, it's 2 chapters. So one is the X-ray machine and components and functions. So we'll get a little bit more deeper into the X-ray machine and the tube head and what are the parts of the tube head and what each one of them do. And the next one is the factors that affect the radiology. And we'll talk a little bit about how our exposures are affected based on time, kilovoltage, milliamperage, and all of these other things that we have, and how can we get the best coverage, the best radiology exposure that we can get. Okay, so moving on. The components of the radiology, the X-ray machine, we already know. So A is what? A is control panel, exactly. So it controls, the MA, the KV, P, and exposure time. So MA stands for what? Milliamperage, which we'll do in a little bit. KV is kilovoltage, and then P is the peak, so kilovoltage peak. And then exposure time, which would be in milliseconds. Definitely, it has the on and off switch, and it is required by law when you press the button to do the peep, the signal. So when you press the X-ray, you hear that peep sound. So it is actually required by law to give that sound. Number B is the arm, the extension. I'm sorry. That is wrong. This is wrong. This is C. I don't know how this happened. So correct that on your side if you can. I don't think you can because this is, well, just do C. Yeah, just type C before that. So yeah, that's what happens when you work late.
Oh, okay. So the bullets under it are also for.
Yeah, like C is not right now. C is B. All of that. Just So, I mean, don't worry about these A and B. So let's put here A is control panel, right? We know that. B is the extension arm. C is the tube head. And D is correct. Are we good about that, guys? So just C and B are, wrong. I mean, I can just, whoops, not do that. And delete this. Delete that. Get that here. And hit an enter here. Do this. And fixed. So anyway, well, so we know what B is. B is the extension arms. It's usually hollow to hold the wires. And we know we want to fold it whenever you're done. And most probably you guys doing that. Whenever you're done with your lab, you want to fold it up so it will not get, what do you call it? Like the springs that are in it will keep working correctly so you can extend it and work with it and it will be stable. So we have to always fold it back when we're done. And then C is the tube head, which contains the X-ray tube, which we'll talk about. So we have tube head and we have the tube itself, the X-ray tube. And then D is, PID, which is position indicator or indicating device. Okay, we already talked about that before in the first exam, and this is just a refresher because we're going to talk a little bit about each part. So control panel, the extension arm, and the tube head. Okay, all good. We know what they do. And PID also called what? No, other than PID and cone, right? A cone. Oh, position indicating cone. Okay. That is good. Okay, now we'll talk about each part of the, well, not all of them, but most of them, the X-ray machine. So the control panel, as we said, it controls the exposure time, controls the MA, and controls the KVP. Um, so exposure time is measured. This is the control panel. I mean, it can be all different, but that's the kind of usual look of it. Uh, Exposure time is measured usually by ms, which means, huh? Milliseconds, right? So like it's 0 point something of the second. So usually when you turn that machine on and you see the numbers that are on here, right? This is by millisecond. So this definitely is the amount of time that the X-ray will be produced. And a lot of the X-ray devices that we have nowadays, this is the only thing that we actually can control, right? So when you're trying to, you got a child and you want to change the controls, right? You pick the child option on the control panel, and what will happen is what, when you change these options here, if it's a child or adult, what will happen usually? The numbers will change, right? So again, if you like for a posterior tooth, the numbers are more, right? The exposure time. So that's why we're saying that's usually the main thing that we can control, because usually the kilovoltage and milliamperage, we cannot change them. We can only change the exposure time. And a lot of time, again, we don't have to change it manually. We can just choose, is it a posterior tooth or is it an anterior tooth? Is it maxillary? Is it mandibular? Is it a bite wing or not? And that's why it's the only measure that we can actually control by us, the operator. Okay. Another thing that is on the control panel is the MA, and the MA stands for milliamperage or milliampere. And this is about electricity. So, because we produce radiology with electricity, and the two factors that we can control within the electricity is the amperage and the voltage. What is the kilovoltage here in the United States? 110, right? I think in other countries it's 220, right? Kilovolt. It's just that the electricity that we get here from the sockets. So it's usually 110, and I think it's 220 for if you have a stove or something like that, or the AC unit. It requires more kilovoltage. Anyway, so an amperage, again, this is what we regulate to make sure we get a great or good X-ray. And the milliamperage control that we have. And when you say milli, that means what? One, huh? One, one on 1,000, right? One on 1,000. And same thing, millisecond is one on 1,000. Milli, right? Yeah, millimeter. Yes. So one on 1,000. The milliamperage controls the number of electrons that actually goes out in the radiology and the X-ray, which is the quantity. How much we know when we produce X-ray, we need electrons to fly out from the cathode towards the anode, right? And these electrons will actually produce the X-ray. When they're stopped and they're slowed down, they'll produce the X-ray. So one thing to control in our control panel is the number of these electrons. But again, as I said, a lot of times our machines come with a certain and specific number that is preset for our machine that we do not control really. Okay. If you increase the milliamperage, you're going to increase the electrons, okay? And then the regular range of our X-ray machine, it will run from 4 all the way to 15 milliamperage. So if you look here on our control panel, what is the milliamperage here? Huh? 7, right? 7 milliamperage. And again, if you look at the machines that we have in the lab, I think it's also 7 milliamperage as well. So again, a lot of times nowadays with the newer machines and newer devices, the milliamperage and even the kilovoltage that we're going to talk about now, it's already preset. We don't play with these anymore. But we need to know how they affect our radiology, how they affect our exposure and the image afterwards. And sometimes the machine will control that by just, when you press on one of these, it might change automatically the kilovoltage or milliamperage based on the region. But again, as I said, most of the machines nowadays, they're already preset kilovoltage, which is usually 70 and usually 7 milliamperage, and that's it. You just control the timing, okay? So we know that is one. And then kVp, that is the kilovoltage, and that is kilovolts. And then the P is for peak. If the milliamperage, controls the number of electrons, kilovoltage controls or if milliamperage controls the quantity, kilovoltage controls the quality, which means the speed. Yes, the speed of electrons. The kilovoltage actually controls the speed of electrons. We'll talk about that a little bit more in when we look at the actual tube head. So increase the speed, or definitely increase the kilovoltage, will increase the speed, increase penetration power, and increase the energy. And when we say here P, kilovoltage P, because the kilovoltage can range. So even if it's, for example, in this device, when they write it here, and we see that it's 70, right? Or 60 to 70. It can go from 40 all the way to 70, or from even less than that. So it can range, but the peak, the most amount that it can get to is 70 kilovoltage, okay? With milliamperage is fixed. It's just that specific number that they put. So we don't have like a milliamperage peak. We just have a milliamperage, okay? And then with a kilovoltage, we have a kilovoltage and kilovoltage peak. Does that make sense? We're good so far? Okay. So let's just talk here about the tube head and how the X-ray is formed again, because I think we didn't get that completely out of the way. This is the tube head. All of this big thing is the tube head, right? But then we have inside of the tube head, we have the X-ray tube itself, which is technically like a light bulb here. Do you see this? This is the actual tube, X-ray tube that is inside of the tube head. Okay, so this next picture is for the X-ray tube, not the tube head. And this is the tube head that has the tube. Does that make sense? Huh? The X-ray tube is inside of the tube head, right? Easy? Yeah, so this picture is just for this thing here that is inside, not the all of it. So just make a difference. This is a tube head that has all of these parts and the PID and the collimator and all of the other things and the oil. And the tube, the X-ray tube itself is just the one that has the cathode and the anode mainly. Okay? So let's talk about how the X-ray is going to form. Okay. We have a cathode, right? And the cathode is what is negatively charged. Remember, you want to get A positive, right? Or A plus, not a C minus. Just to remember, A anode is always positive, and C cathode, which is negatively charged. So when we get the electricity through this filament here, we start making electrons, okay? So a cloud of electrons will be running here. That's good. Then we have this condensing, or what is the word? Collecting mirror, not mirror, cap. I have a better word for it there. This would focus these electrons, and then with the amount of kV, it will shoot these electrons towards what? The anode, right? So the amount of electrons that will be here, that will form here when we start the X-ray, depends on the milliamperage, right? How much milliamperage? Because milliamperage is about quantity, right? And then again, these electrons will be just flying here in a cloud, and then we will apply kilovoltage, or the voltage technically, and the voltage would shoot these electrons really fast towards where? The anode, and specifically the target in the anode, which is a tungsten plate. When these electrons hit the anode here, or the target, these electrons will be stopping or will be slowing down. When they stop or they slow down, an energy will be released, and that is the X-ray that will come out of the tube here towards the PID. Okay? Clear? No, not that much? Okay. Well, I think we're getting there. We're getting there in a little bit. So one thing also, because I think we're going to mention that. So when we want our filaments to heat up, again, it's just like a light bulb, right? The light bulb has a filament in it, and it heats up to bring up light. So same thing with this filament. We want to heat it up to bring up electrons, right? So when we want to heat that up, we want just a little bit of the kilovoltage. We don't want a lot of volts in there. So we have a step down transformer that will reduce the regular electricity that come from the socket to a smaller amount of voltage, which is about 5 volts. So 5 volts is just enough for the filaments to heat up and to produce what? Electrons. Then, because we want to shoot these electrons all the way to the anode, we'll use a step-up transformer that will raise up the voltage all the way to 70 kilovoltage, right? And shoot them up. And that's what the step-down transformer is used for, and the step-up transformer is used for. Let's see what else that we have. This is all surrounded by insulating oil, so it would dissipate heat and also can do some filtration of any X-ray that can escape through it. We have a seal here just to seal the oil from going out. And then also we have an opening in there where the X-ray would actually come from. We have a collimator that will shape the X-ray. So we can have it as circle or rectangle. And then we have the position indicating device that comes out of here. Again, we're going to talk about these a little bit more, I guess, in depth as we, yeah. Yes, yeah, that's an insulating oil, exactly. Well, I think in the picture, it's just, to get you more. Yeah, I'm not sure how much oil would be in there. I'm sure it's different from one machine to the other. Huh? Yeah, right. And again, this is just a closer picture or diagram. You guys definitely need to know these markings. So labeling of all of that here, you need to know that. The X-ray tube itself, this is just a closer picture. Again, we have the filament, which is also tungsten. And then we have the focusing cup that will shoot the electrons towards the targets that is in the anode, right? And then you have your X-ray that will come through it. Okay, so this is what we're talking about, the X-ray production. So technically, again, in simple words, X-ray produced when stream of high-speed electrons, right, that came out from where? The cathode, right, from here, are stopped or slowed down where? In the anode target, correct? So it's just you have electrons that you're shooting towards a target, and once these anode hit the target, instead of making sound or heat, well, they make all of that most probably, but they will also produce some energy, and that energy is considered radiology or X-ray. So again, to put it more in terms, so electron cloud that is made by the filament in the cathode, right? So we have electron cloud made by the filament in the cathode, focused, sped up, and accelerated towards the yes, anode target. Yes, that's okay. And hitting the target will slow or stop these electrons, and the energy release is X-ray. Does that make sense now? Okay, and again, this is how X-ray is produced. You have the filaments that will give us some electron cloud, and then we have a focusing cup that will, with the help of the voltage, will speed it and hit the anode, which is the target. Once they hit the target, they'll slow down or stop, and this will get the radiology made, X-ray made. Okay, all makes sense, hopefully. You can explain it to someone? Okay. Well, you need to be able to explain it to someone that means you understand it. So hopefully this is clear enough and simple enough. Just a lot of electrons forming here, a focusing cup to focus them, a voltage to throw them really quick into the target. When they stop here, they produce energy that is X-ray. Yeah. Okay. So you have to know the parts. Yeah. Mainly about this the main picture here. Okay. So 3 conditions that we have to actually get the X-ray produced. Source of electrons, right? Which is from the filament, which is from what? The milliamperage, right? The amperage. High voltage. This would provide us speed and quality. And then a strong target that can withstand these being hit on it, right? Which is the tungsten target on the anode. Okay, and again, this is a picture of actual tube, X-ray tube, where you can see it's just like a light bulb, maybe the older types of light bulbs in a way. Anyway, definitely it's vacuum, so there's no air inside here. All good. Okay, remember the transformers that I was talking about? These will change technically the voltage. Okay, we have a step-down transformer that will reduce the voltage. I didn't put voltage here. I just put volts to make it smaller. Okay, to about 5 volt, heating the I cannot even hear you guys. Filament, right? It heat up the filament to create the electron cloud. And then we have a step-up transformer that makes the volt all the way to when we say kilovolts, that means 1,000. So when we say 50 kilovolts, that means 50,000 kilovolts. That is a lot of voltage, right? And this would propel the electrons towards the anode. So, that's okay. Same thing. No difference. Anode, the target, and the anode, that's okay. Are we good with these guys? Again, we're still talking about the tube head components. What do we have inside of this tube head, which we explained a little bit before. So we talked about all of that here, right? This is the filament, and we get the step-down transformer to make the filament heat up and produce electrons, and then the step-up transformer to get the voltage much higher so we can speed up the electrons to go and hit the target. Okay, The cathode, as we said, it is negatively charged. You always want to get an A plus, not C minus. So this would provide the electrons with the tungsten filament and the molybdenum collecting or focusing cup. That's the material that is the cup made of. The anode, on the other hand, will stop or slow the electrons, right? So cathode supply electrons, anode would stop or slow the electrons. So it has a copper bar with a tungsten plate that we call the, yes, you got this time. And then blank is a small area on the target, which with the focusing cup of the electrons will beam. That is the, yes, who said that? Yes, that is the focal spot. Are we good here? We're relating to what we saw in the pictures there. Tungsten filament, the focusing cup, and then we have targets. So this is the copper bar. So when you look at this, this is the copper bar, and then you have the tungsten target inside of there, and then you have that small area there that's the focal spot where all of the x-rays will be kind of condensed into or focused to, and that's where we get the x-ray. Okay, so we're just talking about that picture still. That is all parts of the tube head components. So we have excuse me, also insulating oil that is for filtration and heat reduction, right? We have aluminum discs. Did you see the aluminum discs on the picture? Right, these aluminum discs there. And these would reduce what? Yes, long wavelengths, because we are not using the long wavelengths. We only want the short one that has more energy in it. And again, this is relating to what we talked about before, you know, the material for exam 1. We talked about the long wavelengths and short wavelengths and what we call them. So the aluminum discs will reduce or filter out all of the long wavelengths that we do not need, because they would not produce any good x-ray for us. So why exposing the patient to more radiology or to more x-ray radiation if we can stop that, right? If we don't use it in the first place. So this will filter out, so reduce the radiation for the patient. And the other thing is the collimator. And this controls the shape and size of the x-ray. And by that, it will reduce the scattered radiation. Oh, yeah. I was going to ask about that, but I didn't remember what I put there. So the collimator, again, which we saw already on the device there, all the way up, if we go back, this is the collimator, right? So the collimator is that last window that the x-ray will go through. So it goes through here, it goes through the aluminum discs, and then it goes through that small opening that will let it, go through it and then go to the PID. The collimator is responsible for the shape and size of the x-ray beam. So if you look here, we actually have, this is the collimator. So this is the tube, x-ray tube, and this is the collimator at the beginning of the PID. And it can be a circular or it can be rectangle. You would not see a lot of rectangular ones, although they're actually better, because you can see if it was circular, you'll get much more exposure to the patient, right, than if it was rectangular, correct? But the problem with the rectangular one is that it's hard not to miss the x-ray. You'll have a lot of cone cuts and you'll have a lot of missing parts, because you have to really aim it well. Right now, you're aiming the X-rays, and you're already seeing how sometimes it's not easy. So with having a rectangular collimator and definitely PID also, it will make it harder for you to shoot the X-ray correctly, but at the same time, it exposes the patient to much less exposure, up to 70% less exposure if you're using the rectangular uh, collimator and rectangular PID. What in the regulations, the final opening when the X-ray, go out of the PID, it must be 2.75 inch or 7 centimeters at the patient end, which is here. It should not be longer or wider, bigger diameter than this. And this is again in the regulations. So when manufacturers are producing these, and they do the collimator and they put the PID, they have to make sure the collimator is small enough to produce that much X-ray at the end of the PID. Okay? All makes sense? Yes, all good? Any questions so far? Okay. Moving on. We're still within the tube head components, the sinks, and the parts that we have. So the PID, which we know, the position indicating device, this is to direct the X-ray beam, the primary one. It can be also round or rectangular, similar to collimator. So if you have a rectangular collimator, you have rectangular PID, and so on and so forth. It can have different lengths, right? As you can see in the picture. And this, by the way, this is the rectangular one. You can see it's almost the same size of your film. And we can even have some of these devices that we can put on our circular ones that will make them rectangular ones. Yeah, so just to reduce, but again, most probably you'll not see it in any office, because again, it's harder to really shoot with a rectangular one. And now with the digital imaging and the digital, X-ray devices, the X-rays became much less harmful, because we're not exposing a lot to the patient. So anyway, but again, this can produce much less exposure. And the longer the PID, okay, the longer the PID, the better for our picture. And also the better reduction of the X-ray. Because again, if you look at this picture, if we have the source here that is more farther, and we have all of this as PID, the divergence of the X-ray will be less. It will not go wider. If we have it shorter, so this is like a 16-inch PID, and you can see the lines that goes from there will be much narrower than if we have it on the 8-inch PID. Because it would reduce the exposure to the patient. It is much less exposure to the patient than the circular one. So if you see this picture again, you see how much less exposure we're giving than with the circular one. You can see that all of this is just missing X-ray that we're not using. While here we're much smaller. Now, like this is about 2.75 inch, while this one is just 2 inches by 1.5 inch. So it's much more smaller. It's almost the size of the film. Is that good, guys? All clear? So longer the PID, the better for us. Less divergence of X-ray, reduced patient radiation, and it even gives us sharper image, as we'll see. If you remember when we talked about shadow production, we talked about the source and film and object length, all of these things we talked about before. So, any questions? We're good? We're still good? Okay. I wanted to show you this video here.
Protect your patient's necessary exposure to ionizing radiation and improve the diagnostic quality of your.
So this is a device that is added to the regular circular PIDs to make them rectangular. And you'll see it has a nice trick for you to make sure that you're getting the correct aiming all the time.
X-ray images with TrueAlign from Interactive Diagnostic Imagery. TrueAlign is a rectangular collimator that slides over the cone of your existing X-ray system to shape and control the size of the X-ray beam to the size of the receptor. A round cone acts like a shotgun as radiation exits the cone in a spreading pattern. Only about 10% of the beam actually hits the receptor. Many photons are scattered into the patient's tissues or reflected back onto the receptor as noise or fog, compromising the image resolution and diminishing the diagnostic quality. TrueAlign acts like the scope on a rifle. The beam is only 2% larger than the receptor. By drastically reducing scatter radiation and collimating the beam, the images, regardless of machine or receptor type, are clearer and crisper and contain greater information, as shown here in this side-by-side comparison. This translates into improved patient care and increased practice revenue. TrueAlign retrofits to any round cone with a diameter of 2.5 to 3 inches. There's no need to remove the existing cone. Simply slide the TrueAlign on and tighten. It literally installs in seconds. TrueAlign features an internal LED laser that ensures perfect alignment and no guesswork, eliminating cone cuts and retakes. When the laser and ring reflector are exactly aligned, the ring magnetically connects. The green lights on the front edge of the device illuminate, and the unit.
So it has like a magnet on the ring set that they have with it. And again, as you heard, it has a laser to it, so it will, when you are actually completely perfectly aligned, it will match up and it will get together. So it's much, you're there's no guesswork anymore. You're 100% going to hit that film. Okay.
It beeps, indicating a
Huh? Right. But I haven't seen this in person because it's really rarely to see people doing that. I mean, investing money in that just because they want to protect the patient. So yeah, it's just, again, with the new X-ray machines and digital radiology, we're getting much less exposure to patients anyway.
perfect image every time. Even a novice can take perfect images in just minutes, drastically reducing your staff training time. Here's what leading dental professionals and organizations.
They say it's really nice and really good, and yeah. So anyway, that's one type of the devices that we can add there. Okay, we're good so far. Why can't we get that small? Okay. Now we're moving on to the next chapter, which are the factors that affect the radiographic quality. Okay. So definitely when we are, taking an X-ray, we have to always think about the ALARA concept, which you remember, right? As low as reasonably achievable. Exactly. That means we're going to change the measurements for exposure depending on the patient and depending on the case and the teeth location and all of that. But at the same time, we want to make sure that we do not expose our patients to extra radiology that they don't need. And because radiology is harmful no matter what amount of exposure you want to give, it's harmful anyway. It's not beneficial to the patient. So we want to get as good quality as we can when we're doing our X-ray. So we want to have the highest diagnostic quality at the lowest possible radiation dose. So some things that we all agree on when we take, just a regular accepted X-ray that can be used in an office. Definitely, we want to see all of the parts that we're trying to shoot, right? So all of these parts that we're trying to shoot, for example, again, if we're doing like a posterior molar exposure, we want to see all of these, and they should be all closer to the actual size and shape of the tooth. So they're not blurred, they're not enlarged, we're not having a cone cut. That's one thing. all of the area also shown with all of the other surroundings. So for example, again, for a PA, we want to see more of the periapical area, right? A little bit above the roots of the teeth. So that's another thing. And then definitely we wanted to have it as a high quality, good density, good contrast, and no errors. So these are just general requirements for a good, acceptable X-ray that is of a diagnostic quality that we can actually look at. And sometimes I'm sure Dr. Spina has already told you, but you know, we don't take X-rays that are perfect all the time in the offices. They're always patient. They have different teeth and different margins, and you're not going to get it always perfect. We're humans, right? So even if we get it wrong or we did some cone cut, sometimes we're not going to redo the X-ray because it's still out of, it's still of a good diagnostic quality. We can see the teeth that we want. Maybe we don't see other tooth that can be better if we can see it, but it's just good enough for our work. So we don't need to expose the patient to another X-ray. And that's why, again, radiology, X-rays, radiographs needs to be prescribed by the dentist, not just taken right away. Okay. Anyway, moving on. So this is a good X-ray that is considered of a good radiographic, feature. You can see, we can see all the teeth that we want to take. This is a premolar shot. We can see beyond them a little bit, and the tissues that surround them, they look the size and the shape like the normal teeth, right? We don't have any cone cuts, any blurring, any elongation, shortening, nothing there. So this is a good X-ray. Now let's see the terminology. You guys have that on the side. So try to guess these for a minute here, and then we'll try to get that together. This is when we're talking about the image quality generally with X-ray. Did we guess them all? Okay. Let's see. So blank is the detail and clarity of the outlines of the structures on a radiograph. Sharpness, exactly. For some reason, this is not working. Okay. And then blank is the film blackening, degree of darkness, amount of light transmitted through the film. Density, exactly. And this would be contrast, how dark and light areas are separated. And then the last two, yes. So these are things that we think about when we are taking an X-ray, how to describe the quality of our X-ray. Again, we want to get a good quality of X-ray. So density, again, how dark it is, and it is usually related to the amount of electrons that we're actually shooting. So how many electrons we're shooting, that will, again, quantity, how much they are. So the more they are, the more dense the X-ray would be. The less and the less would be. So that is related to what? Kilovoltage or milliamperage? Milliamperage, right? Because we're talking about quantity. Contrast usually is the quality, and it's more related to the kilovoltage. So if we look at this here on the side, a high contrast when we don't see a lot of grayish areas. Okay? This is important to understand or know. High contrast mean black, white, and some gray, just not that many. Low contrast is the one that you have long scale, so you have a lot of grayish areas in there. That's why in dentistry, when we say 50 Shades of Gray. We think about that. It's an inside dental joke. Right? Okay. We're good with these terminology, right? And I'm going to talk a little bit about how we can, what factors affect what, okay? Here in this picture, talking about contrast, what do you guys think? Okay. I don't have to teach anymore. You guys know all of that. So, right, it's a low contrast because you see a lot of grayish area in there, and it's high because it's just mainly black and white. And in here, this is A is it more dense or less dense? Is it overexposed or underexposed? A is overexposed? Okay. Underexposed. So we did not shoot enough X-rays, right? Again, density is about the quantity of X-ray, how much electrons we're shooting. We didn't shoot enough here. So it's less dense, right? We didn't shoot enough X-ray to it. We did not expose it enough, right? So like exposure time was too short, for example. We just hit and, lift our finger out of the button. So it's less dense. And the other one is overexposed and darker, which means more dense. So underexposed, more light. Too light. And then overexposed is too dark. Good, we got that concept? Just let us go. Okay. Exposure factors and how they interact or how they affect contrast and density. As I said, density is about amount of electrons. So usually it's more related in a more direct way to the milliamperage. So you increase the milliamperage, you increase the electrons, and you increase the density, and you make it what? Darker. Less milliamperage, less density, lighter, right? The more time that you expose the film, the more dark it will be, the more dense it will be, correct? Just again, like the picture that we saw. Overexposed. We expose it too long. Okay. The less time, the less dense, the less, the lighter. The more kilovoltage, the darker it is, the less kilovoltage. So density is a direct relationship. Whenever you increase something, density will increase, right? Decrease something, density would decrease with milliamperage, time, and kilovoltage, correct? Now, when we look at contrast, it doesn't relate directly to the amount of X-ray or electrons produced. So we're not talking here about the milliamperage with the contrast. We're talking more about time, kilovoltage. So if you look closely, if we increase time, you'll actually have less contrast. And if we decrease time, you will still have less contrast. Because still the areas are not clearly, dark or black, yeah, or gray. We don't have a lot of, we have a lot of grayish area. It's not clear completely. Same thing with the kilovoltage. If you increase the kilovoltage, you still have a decreased contrast, okay? Because we hit it with too much power that we didn't get just enough power to get these details that we want. If we reduce the kilovoltage, so it's an inverse relationship with the voltage. If we have scattered radiation, definitely we'll have lower contrast because we'll have a lot of grayish areas. If we have less scattered radiation, then we have more contrast because less. So you need to really go back to this and look at it. Yes, you need to know these. Definitely. Okay. Continuing with factors that influence the exposure. Now here we're talking about sharpness. So the focal spot, remember the focal spot, right? Is it smaller better or bigger better? Smaller, right? Again, this we talked about before when we talked about shadow forming. So the larger will create a numbera, okay? And the numbera is actually the partial shadows that surrounds the object. So if you look here at this picture, that's the numbera here. That is technically just shadows that are extra that surrounds the actual picture. Okay? So the bigger your focal spot, the worse it will be. Okay? That's why we want it to be smaller. Movement definitely can, again, we're talking here about sharpness because the more sharp it is, the less shadows around it. Movement, if the patient moves, definitely there will be blurred image like you see here. The patient moves or our tube head is not fixed correctly, so we'll see that. The film crystals, you know, if they are smaller, will be more sharp. Smaller they are, the sharper they are. Just like the, think about it as the resolution, like on your screens, like 4K is more resolution, the sharper the image, right? And so on and so forth, less and less. And then intensifying screens, these will decrease sharpness. And intensifying screens are things that we use with extraoral x-rays. When we use like panoramic x-ray or cephalometric x-ray. So we're not talking about these yet, but know that intensifying screen that is used with the extraoral x-rays will decrease sharpness. We're almost there, guys. Almost there. Okay. Magnification. This is another problem or issue that can happen. So definitely it's the increase of the image size on the x-ray compared to the actual size. So if you look here, let's see, mostly influenced by the target object distance and the object film distance. Again, this is going back to what we talked about before when we talked about the shadow forming. So the target, which is the anode, technically distance determined by the length of, so, PID, exactly. So in our machines, the target object distance is just how the PID, the length of the PID. Is it 8? Is it 16? The film object distance should be kept at minimum. We want the film really close to the tooth as much as we can, if we can. This would reduce the magnification. Again, you can see here if our distance is far, which means our PID is longer, we'll have less divergence of the x-ray and we'll have more correct image. But if we have it closer, like at 8, you can see the image is magnified a little bit. And same thing again, the image receptor and the object, we want them to be as close as possible. We talked a lot about that in with the last exam. Okay. Distortion is just that kind of magnification, but it's just unequal magnification. So this can happen when the film is not parallel to the object. So you can see this is the tooth and your film is a little bit sideways. Again, we do this. If we do this, we have to take it with a bisecting technique, not paralleling technique. So if the film is not parallel to the object, you hit distortion. Or if the X-ray beam is not perpendicular to the object and the film receptor, you also might get distortion, which is, again, parts of the image will be bigger than the other parts. And sometimes like this can be elongation or foreshortening, maybe even. All good? Okay. We're almost there, almost there. This one we'll see if you guys know math. Yeah, unfortunately. Right? So, the inverse square law. So, let's read that together. You love math? Okay, let's see. The intensity of the radiation varies inversely as the square of the distance of its source. So that means the more distance, the more the X-ray is away from the object, the less the density, right? Just like a light. If you turn on a light and you're closer to an area, you can see better because you have better light. And if you go further from there, then that means your light intensity is less, right? Correct? Just like a regular light. The further that you are, the less the intensity it is. But it actually, more than that, it is also doubled. So it's the square of the distance. So when you look at this picture here, you see now we have the film, or we have, like, for example, yeah, the patient is here. And if we double the distance, if it's double the distance, the intensity will be lowered by 4, not by 2. So it's the square of it. Does that make sense? Yeah? Okay. We'll go with that. So when we look here, we say if the target film distance, the anode, and film distance is doubled, so by 2, the intensity decreases or increases? Decreases by 4. If it's doubled, then this will be square of 2, which is 4. If we want to maintain the same density, for example, again, we went farther, but we still want to keep the same density, what we can do, the exposure time can be increased or decreased. Huh? If we want more density, right? We got lower density by 4. So we need more density by 4. So we need to give time more. How many times? 4 times, right? 4 times the time. So if we expose here at the beginning for 1 second, for example, right? If we expose here for 1 second and we got density, good density, to get the same density here, we have to expose for 2, well, let's say expose 2 seconds here. You have to expose for 4 seconds on the other side, right? Or if it's 3 here, then it'll be 8 there. Does that make sense? Yes, we'll just say anything to get you done. Okay. So the inverse square can be written as this. You can see this is a fractional. I don't know what you call this, but it's fraction, right? The fractions. I don't know the math term in English maybe, but it's an fractions, right? Yeah, fractions or square. I don't know. Inequality. So you can see you have the original density on the new density equals the new distance square on the original distance square. And same thing for the time. And this is our question. Let's see how many of you guys can get this. Yes. So a dental radiographer removes an 8-inch PID and replaces a 16-inch. So this is the distance, right, that we have. So if you put that in here, the old distance is 8. The new distance is 16, right? What is the effect on the intensity? How? By what? What is the effect of the intensity? Huh? Huh? You have to do the math. If you, huh? What? If you did this right, you'll gain one of Nima's gifts. HCC label. No, and it's not even this. A bad HCC water bottle that you're not going to use. Maybe, right? A lip balm, I guess. And then a pen that has a game into it. It has a small game, like it has a, yeah, like a, what do you call these? Like a small ball that you have to go through. Yeah.
So, to get it, you would have to plug into
Yes, definitely. Yeah, I mean, you just do the what by for what decreased, and how did you do that? Can you do that on the there? Go for it, Karen. Let's see. I think we have the markers there. Yeah. So, right.
Don't know what those numbers are.
Yes.
Well, I know 64, but 16 squared was something like 56.
Yeah.
Which equals.
So, how do you apply it to that?
Well, it said, okay, now look.
You're there.
Okay, I am here.
Yeah,
I'm
but
here. This is formula said new distance over old distance squared equals,
original intensity on the new intensity.
Yeah, yeah.
So, what is the new intensity? How can, yeah, we're asking about the new intensity, like what it would be.
What would be the new intensity?
You're right, but I want you to be, you just have one more thing to kind of almost, not really more math, but just to, huh?
Oh, so the new intensity is 64. No? It says
Just to make it more.
okay, hold on.
So we said this would be the old intensity, the new intensity, the original. That's the original. So we say if the original was 1, right?
Yeah.
What will be the new one?
No, don't do that. Okay.
Yeah, and then you can just do this is 1, right? And this is 2.
Yeah.
So this 2 by 2 would be 4.
So
So just flip it.
4.
Equals 1 on 4. So it's
Wait. Okay, hold on. No, you stop, Alex. Go away. Go away. We're doing maths here. 1 over x equals 4 over 1. Stop, Alex.
Cross multiply. Yes.
Okay, I'm gonna get there. It's been a while.
Yeah, there you go.
Yeah, here we go. Yes, let's give her a round of applause. Yes, thank
I just had to. Okay,
you.
whatever.
No round.
This I learned like 20 years ago.
Okay, that's good. That's good. Well done. So it's a quarter of the original one, right? So that's the intensity, which is what you said, like decreased by 4. Yay! Well done. Good job. Let's give. Huh? We'll talk about it. What do you want?
Oh, I don't know. I'll do, what's this?
Lip balm.
No, water bottle.
Water bottle.
And when I'm drinking from it, like Monday through
You just do the math. I mean, technically, you do the math. I know you guys going to ask me, and I was thinking, should I give them that? Maybe an extra question. Not like a question. So if you want to do it, you do. Yeah. That's that kind of thing. So you just do again. You just plug in the numbers. You just plug in the numbers, and it will magically work. Yeah, like when I did this. Well, yeah, if you erase this, just because it's easier, and so just to make it easier for you to do the count, instead of having to do the square of 8 and the square of 16, just what do you call them? I don't know in English specifically. Yeah, simplify, right? So how many 8s are in 16? There are 2. And how many 8s are in 8? There's 1. So it would be quickly 1 on 2, right? And then squared. So 1 squared is 1, and 2 squared is 4, right? So we'll have 1 on x equal 4 on 1. And then you just, yeah. Does it make sense? Yeah. Yeah. Right? So if we are talking about time, it will be kind of the same way, right?
New intensity. I mean sorry, the original
We just put it as one.
would
Yeah.
just be one.
Yeah, was it the? Yeah, technically. So be able to count. Yeah. You got there almost, but it's we. Okay, well, this is done with that, and then we have the exposure charts, which are these things that you press a button to make sure you get the correct one, the correct exposure for your patient, right? Depending on the area that you're exposing. So all of the machines now come with this, and you don't have to do any time or kilovoltage or milliamperage, and that is that. Any questions? Huh? You don't do that? No, guys? You don't change the time here? Do yeah, do you change the time? Exactly. So that's the only reason, maybe, because we want to expose the least amount of exposure for us as teaching. But when you go out there, you have to change it. Yeah. We usually try to get it the lower exposure. Are we done? Okay, well, I guess. 1 second. So I'm going to share with you again the same game. So we'll do another tournament. And all it's a Sunday. Make sure that you log in and make sure you do it. And most probably I'm going to add another game to it. Okay, and then, huh? Same games with a one more extra maybe. Let me just look and see. Yes, and make sure that you guys do the toothbrush thing. Order it just to make sure that we don't have any problems with the ordering. Let me just stop the recording here for a second. You can. That's it, guys. You can leave. I mean, I'm just stop.